Thank you, Tim, for the introduction. So, as you mentioned, it's kind of looking at the application of bioenergy crops in kind of a different way. So the interest of our work is looking at not only bioenergy crop integration into the agricultural system from a nutrient reduction viewpoint, but also more so as a resource recovering landscape system. So this kind of not only helps reach the goals of nutrient reduction for both state and national levels, but also approaches the bioenergy cellulosic feedstock mandates of the Energy Independence and Security Act. So coming from central Illinois, where the main dominant crop cover is some form of agriculture, which this land then feeds into a lot of these bigger water systems, there's a need to think about how to sustain these agricultural systems, not only to promote growth in the future, but also to sort of mitigate the environmental impacts that these practices have. So bioenergy crop integration has the ability to sustain these systems by both promoting or by the inclusion of these additional regulating services, which is kind of shown here in this graph here, water quality, carbon sequestration, that sort of thing, but also to optimize your provisioning services, so your food, your energy, and conservation. But the key here is the strategic placement of these bioenergy cropping systems within the landscape at these multiple scales. And so, for instance, if we look at our field site in Fairbury, Illinois here, we have this sort of upland section of our field is considered marginal. And in this case, marginal is classified as either environmentally, is susceptible to environmental degradation, has low crop productivity, or both. And so this particular area here is susceptible to nitrate leaching, has a high risk for runoff, and has low crop productivity. And so these are the type of areas that then we target for energy crop integration to have the highest feedback in terms of nitrogen reduction as well as nutrient recovery. And then we can kind of scale this up to the watershed level. So this is the Indian Creek. It's about 87% to 90% land covers ag. And this feeds into the Vermilion River watershed, which is predominantly nitrate impaired, which then eventually feeds into the Illinois River, into the Mississippi, and into the Gulf. And so which in all these systems are impaired in some way, shape, or form. And so the focus of this talk will focus not only sort of verifying this cropping system integration as a viable conservation practice, but also economically as a bioenergy cropping system. So this sort of gives you a visualization of the integration of these bioenergy systems within the agricultural landscape. So ideally, you'd have a grain crop that's kind of upslope of your bioenergy crop here. So the fertilizer that's applied, any of those nutrients that are leached that kind of run below the root zone of those grain crops then are picked up by your deep-rooting perennial crops before they enter into your stream system. But the catch to this system is you are converting land that is currently under grain crop to bioenergy crop in a corn, soybean dominated system. So how do you convince farmers to do that? And Tim yesterday kind of alluded to this. So this is the spatial variability of net profits for corn grain in our field site prior to any conservation practice implementation. So, and actually last week I learned that Iowa State University is doing a very similar analysis statewide in Iowa, and kind of found the same results, where the same areas that are underproductive time after time are still underproductive year after year. And so one of the main questions is, why do farmers continue to plant in these underproductive lands? And the main reason is crop insurance. And then you have high variability in corn prices. And so that kind of masks these submarginal areas. And so in our field case, the average net profit is positive at $153 per acre. But you can see here the standard deviation is higher than our average. And so this indicates that the farmer is losing some money in this land. And so if we do a geospatial analysis of this map, we find that the farmer on average is losing about $50 per acre in 16% of this field. So these are the orange and red areas here. And so one of the main goals of this bioenergy crop integration is trying to reduce this standard deviation so that you're not losing as much money on the field overall just by targeting these marginal areas. And so how do you do this? So in order to strategically place these crops within the landscape, you kind of have to come up with some field scale monitoring regime. And from here, we can look at areas that are nutrient hotspots. So right here, we can look at soil characteristics, and then we can do some GIS analysis using GPS RTK surveying to determine subsurface and surface flow, and that gives us an idea of where most of this water is running, and therefore where the potential for nitrate leaching is happening. And so from here, then we can place our buffer strip here. And then afterwards, we can use the same monitoring regime then to look at the impacts of willow integration within the system. So one of the main goals of analysis is looking at the impacts of willow integration on the reduction of nitrogen within the agricultural system. So in 2013, this is the year of establishment, but then we copiced at the end of the year. And we are beginning to sort of see some trends in 2014 and 2015. So here, our north fields are sort of our downslope. We added this as kind of our control. This is in our floodplain area. And then our south upslope is our contour sort of experimental plots. And so we see in 2015 there's a statistically significant reduction in nitrogen under willow compared to corn. And we also did soil sampling, which indicated that this reduction wasn't coming from the soil itself. It was potentially coming from that leachate. And for future work, we're going to be doing some isotope tracking to sort of verify this. And so we also see that these are our monitoring wells beyond sort of on the outskirts of our willow plots, and we also see the similar trends in reduction in nitrate in those groundwater systems. So the next step is to look at whether or not the willows are actually taking up this nitrogen, which I kind of got ahead of myself. So again, 2013 was kind of our establishment year, so by 2015, this is our second year. And so willow kind of has an advantage over corn in that it's a perennial crop, and so your nitrate or your nutrient uptake is sort of gradually enhanced with each year, as well as biomass. So in this case, in order to make it comparable to corn, we kind of cut everything in half. And so we see that biomass, which is our green bars here, is still higher than our corn in both of our landscape positions, and we do have a kind of a high uptake of nitrogen as well. Between the two, the average is about 80 kilograms of nitrogen per hectare. And just to make sure that under this new integration system that we're not impacting or increasing, I should say, greenhouse gas emissions, we looked at greenhouse gas emissions from soil respiration under these two cropping systems, and we find in 2015 there's a statistically significant difference in both our methane and nitrous oxide emissions, and this is primarily due to the fact that we're now getting canopy closure. For 2014 and 2013, there's no significant difference between both systems, and kind of this increase over time we're kind of attributing to increase in precipitation, this increase, between all of our years. So the next step is kind of to scale up from the field scale to our watershed scale, and we can't use the same monitoring regime at the field scale because it's too costly. So we used a modeling system, so we use SWATs, their hydrologic model, and we can compare then our business as usual, which uses these this baseline data input, to our future landscape patterns, which we can do using two different strategies. The first one is remote sensing, which predominantly just looks at corn yields over our watershed. And then we also can use soil characteristics, Sergo data, which looks at both crop productivity as well as marginalities. And so from here, then we can determine how they impact our outputs, including commodity yield, water yield, nitrate leaching, sediment transport. So just to give you a little background of how we did this for the soil data, which is primarily what I'm going to talk about instead of the remote sensing analysis. Using Sergo data, we can then classify soil types as either marginal or non-marginal based on predetermined levels. And so this kind of gives us each different layer for marginalities over there. And then we can layer them together to give us a spatially explicit map, which then we can identify our critical source areas. So in this case, predominantly we're looking for either low productivity, which is about 3% of the watershed, or we look at either areas that are susceptible to nitrate leaching or has a couple of extra marginalities, in this case runoff and low crop productivity. So these are the areas here, 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 and along our riparian. So this is sort of the output results of that analysis. You're looking at business as usual to the left and its corresponding outputs, and one of our future landscape patterns on the right. So in this case, we're just looking at that critical source area, that 22% of the watershed that's susceptible to the nitrates runoff and low crop productivity. In this case, this red here is we're just replacing all that land with switchgrass, and as you can see, for nitrates, tile leachate, and sediment yield, you kind of have the reduction in those critical source areas, as well as the rest of the watershed on those outputs, which is good. We also collaborated with a group from the University of Michigan that did all of our pollinator work for us, and this is just sort of a glimpse of his work. So he was using the INVEST model, which is from the natural capital model, their pollinator module. And he finds that there is sort of an increase in pollinator nesting index due to the increase in diversity of habitat. So these are the results of that analysis. And in this case, we're looking at all of the bioenergy crop replacements. So we added switchgrass, willow, and big blue stem. And we're comparing those future landscape patterns. So that 3% of the watershed, which was just your crop index, which is our first column here, and then that second column is those critical source zones. And so we see an average, it's about, so the pluses are mean, the bar is our median. And so we see for nitrate export, there is, if you're just looking at the CPI, which is just your 3% crop productivity index, the increase from business as usual is about 6% for nitrates and about 3% for sediment reduction. But if you increase that to your 20% of the watershed, then you're looking at, I think it's 26 and 30% respectively for nitrate reduction and soil leachate. And then for yield reduction, it's about less than 10%. So now that we've kind of established that as a conservation practice, bioenergy crop integration works, the next step is to actually look at the economics of it. So we use Tim Volk and his team's work, the Willow model 2.0, which looked at the production and transportation costs for a willow production system. In this case, we're looking at what it would be in Illinois based on our work at our field site, as well as recommendation from Tim's team. And we kind of came up with these 3 different scenarios. So our first scenario is our business as usual, where we're just focusing on producing willows as a bioenergy crop commodity, and that's it. And so you have about a 10% headland for equipment maneuvering, and then you have an application of fertilizer at about 112 kilograms of nitrogen per hectare. But then our 2 other scenarios here are our landscape design, and I brought this up on our first slide, but just to go over the difference between business as usual and landscape design in terms of the services that we're expecting to get out of it, and as well as the different goals. So for our landscape design, our first scenario here is a single subfield. So it's the same amount of acreage that we have here, but now we're talking about a subfield that's surrounded by another grain crop. And so we don't have a fertilizer application, we don't have a headland inclusion in there, but it's just a single field. So this has kind of determined that impact of those ecosystem services where you can kind of take advantage of all your field space and kind of reduce the costs of fertilizer application. And then this is kind of the more practical aspect of that is our landscape scenario, where you're taking the same amounts of acreage and you're splitting that amongst several fields in the watershed. And so we looked at 3 different production scenarios. Our minimum was about 2 hectares, and that was based on our watershed analysis of the size of these marginal fields within our landscape. Then we have a 10.1 hectares, which is from Tim's recommendation is kind of their minimum production scale, and then our optimal production scale is 40.5 hectares. And so this gives you sort of a visual of where these marginal fields are located amongst one another, as well as to our theoretical grain depot. So in this case, we're only assuming that the willow that's going to be produced for bioenergy will be kind of used locally. What I don't show here in terms of our results is we also used the biomass logistics model from Idaho National Lab, which kind of gives us that extra transportation costs and refinery costs for sort of moving this bioenergy offsite. So for business as usual and our single subfield cases, in terms of transportation distance, we're primarily looking at Euclidean distances here instead of physical distance for by roads. So we just looked at scenarios that looked at the minimum distance from the grain depot to a field and the maximum distance to a field in the watershed. But for our multiple subfield cases, we use the most likely transfer distance from the depot to any random combination of fields within the watershed. So what are the big points that come out of this? So our first understanding is that we have this sort of economics of scale, that as production scale increases, production costs decrease as expected. And then we also, but that's primarily focusing on those single subfields. If you then look predominantly at our multiple subfields, you kind of have this increase in production costs as production scale increases, and this is primarily due to an increase in transportation distance. So these numbers here indicate the number of fields that were included in each analysis, and so it's kind of an exponential increase in fields just based on the analysis of the size and the number of fields within our watershed system. So another major component is we see that there is a decrease in production costs between business as usual and our single subfield, and that's predominantly because you're saving money on the headlands, so you get to harvest more land, more material, and you're also reducing the cost of fertilizer application. And so the next, oh, I missed a step. Something that should have come up is you should notice that, so this blue bar here is our production costs, and this is sort of our net revenue, which in this case is a cost in the end, because our revenue from production doesn't fully cover the cost for that production. And so we can kind of think of that difference in two ways. So we can look at the opportunity cost. So by replacing willow in place of corn, we do see that when corn yields are low, we do have a fairly substantial positive opportunity cost. However, that's kind of dependent on, field conditions as well as weather conditions. And so the other way of thinking about it is, oh, that should have came up before, is the production of these additional ecosystem services. And so that difference between your sort of break-even point and where we hit that revenue is the gap in which we need to sort of fill with those ecosystem services provided. The other way of looking at it is those ecosystem services can kind of cover the difference between our business as usual and our multiple fields, because the intent of using those multiple fields is to take advantage of those ecosystem services provided. So why are production costs in Illinois generally a lot higher? So we kind of came into this analysis assuming that we're going to have that cost associated with net revenue. And so land costs in Illinois, because of our fertile land, that contributes over our life cycle analysis, that 22 years, about 50 to 60% of that cost. And then that's followed by harvest and transportation costs. And so one of the questions is, okay, if you kind of came into this assuming that production costs were going to be high, why look at this as a conservation practice? And one of the reasons is because having such fertile land means we have, of course, more grain crop productivity, but it also means more nutrient loss from these systems. And so the Midwest has sort of the largest benefit from sort of including these conservation practices. And then we can kind of look at how willow integration sort of stacks up against the other conservation practices that are currently in use. And we see that based on literature results and our fields analysis, we have an idea of how much nutrients are being reduced by willow, as well as the amount of nutrients that are leached from the system without a conservation practice. And using our own net revenues from the eco-willow model, we can kind of estimate what the cost of nitrogen removal would be per kilogram of nitrogen. And so it's about $9 for willows, and this, and compared to cover crop and crop rotation, is much lower. However, you also kind of notice these other conservation practices that are actually more economic compared to willow. And so from this analysis, we can then begin to think, okay, in this case, we're only talking about nitrogen reduction, but how do they stack up against these other potential conservation practices that we can have. And so this kind of came out of the discussion last week at the International Association for Landscape Ecologists, this sort of stacking of ecosystem services, and how if you look at multiple ecosystem services that each of these different conservation practices have, depending on what the farmer needs, depending on what the environment needs. So it's very much site-specific. You can kind of use this as a tool to determine what conservation practices are more applicable to your site. And so the next major component of this is who pays for it. So we kind of talked about it last week, and we kind of alluded to it this week. Is it taxpayers? If so, how? If you're talking about energy crop integration, could it potentially qualify for the CPR program? What about crop insurance? In Iowa, for instance, they're beginning to have discussion about subsidizing these marginal areas. And so could that be a potential for farmers to sort of rethink about planting these marginal areas with grain crop or something else? Or could it be a reallocation of funding? I'm sure as many of you in the room know how sort of costly it is to remove nitrogen from our water resources. And so could it be a reallocation of that funding from just trying to remove these nitrogen from the water, or could you convert that to applying some of these different conservation practices? The other alternative is, could you get that funding from new programs such as carbon exchange or nitrogen exchange systems? So these are the type of questions that we can begin to think about in terms of how to transition from the science and the research of it to more practical applications. So that's it.